Cool. So we're going. I can start. All right. Thanks everybody for coming. This is the robot pathfinding talk, and I realized when I was looking over my slides like 5 minutes before it started that I have a different title for the talk, so that's why I put this up here. But if you really like the stuff in this talk, then you can look up these other things online, and those are kind of like follow-on concepts to this talk. This is like the introduction to robot pathfinding talk, and this is the other stuff here is kind of like the next one of the possible next steps. There's tons of next steps. Robot pathfinding. How do you get? Essentially, robot pathfinding is like how do you get from point A to point B efficiently, or while completing a mission, or basically, hopefully, at the minimum, without bumping into things like obstacles, like tables and chairs and other robots and stuff. So today, I'm going to go quickly. This is a half-hour talk. I'm going to go quickly through a few different things, some at a higher level than others. The slides that I have here were designed for a little bit of a longer talk, so I'm going to be kind of judicious with what I decide to spend time on and what I don't. But the other stuff that's in the talk, like the slides I made available to the conference and stuff, if you like any of this stuff and you want more information about something I didn't talk very much about, then like get the slides and hopefully that will point you in the right direction. So we're going to talk a little bit about kind of the C space versus the workspace, then graphs as tools, and then some data structure stuff. And then we'll talk about a few very, I don't know, canonical search algorithms that we use, and then a little bit more stuff after that. So space versus workspace. Who's ever been in a car before? Raise your hand. Awesome. So your car exists in the 3D world, and it's kind of like a 3D thing. And it's like X, Y, and Z. But your car can also be oriented in different directions. But to determine like how far away is your car from bumping into a wall or something like that, you can like measure that in what we call the workspace, which is just like the 3D world that we all live in. We actually do robot path planning a lot of times in a slightly different space. So where like the space that we live in is kind of X, Y, Z for like, I don't know, that way, and up. The space that we plan in has to do with some of the degrees of freedom of the system. So example for your car, it could be like forward, turning the wheel a certain amount. And those are kind of your inputs to the system. But your car then might exist at an XY point, but it might also have like an angle associated with it. And if you're like in an airplane or something like that, then it might exist at like an XYZ space, but it have an orientation. So one thing that I'm going to gloss over very quickly here is that the workspace, we can visualize the car, and the car is like a geometric object. In the space that we plan in, which we call the configuration space, each configuration, like each way that the car could be in the world, is just a single point in the configuration space. But that's where we actually do robot motion planning. And so if, let's say, we have a simplified car that exists at an X point, a Y point, and now the up axis I'm going to pretend is theta, the direction the car's facing. And if we have the car just kind of somehow rotate in without changing its location, let's say it was a car that has like some really crazy wheels on front and back so it can just like spin in place, then it would kind of be going like up in this theta direction, right? As it's changing from, let's say, facing in 0 to facing in like pi, and then around back to 2 pi, and then it starts coming at the bottom again because like 0 and 2 pi are the same thing. So that space kind of wraps around in the up and down direction, which is representing theta. So if that's cool to you, then I'm glad that I can tell you about it. If that isn't, then that's fine. The rest of the talk, you don't really need to worry about that if you don't want to. But if you do like that stuff, then it can be, the right space to actually do the planning in is something you have to put some thought into. We use graphs to do a lot of planning stuff. And at a basic kind of overview, a graph is like a bunch of dots with some lines between them. Graph theory is the study of graphs. This notation is funky graph theoretic notation and set theoretic notation, which I don't expect this talk is not designed for people that already know what that is. If you already know what that is, that's super cool. I definitely didn't when I was your age, but I learned it eventually. And basically, the big U just means we're unioning a whole bunch of stuff. We're just combining sets together. And the sets that we're combining together are these little tiny sets that only have one thing in them. So we have a bunch of nodes. We have one set containing each of those nodes, like a different set for each node. And then we're combining all of those into a big set. So it's just a fancy way of saying we have a set that contains all of the nodes in it. And then we have edges. Edges are defined by two different nodes. And there's some relationship that this kind of defines between those two nodes, often that we can get like from one to the other one. And then we also have an edge set. So just, again, we're going to union over the set of all of the little sets, each containing one of the edges to get like a big set containing all of the edges. And then this graph is actually just, I don't know, like this is a mathy thing, and I love math. Sometimes we make things more complicated than necessary in order to be super precise. So we say that a graph is defined by a tuple. It's defined by its vertex set or its node set. Vertex is a different word for node, and its edge set. So if you have a node set and you have an edge set, you put them together, then you get a graph. Now, with graphs, there's different ways that these edges can work. So either we can have an undirected graph, which means that if there's some edge from this node to this other node, that also means that we can kind of get from this node back to that node. That's just implied, like it's a symmetric sort of relationship between these two nodes. That's like useful for like walking on sidewalks and stuff. Directed graphs, these edges only go one way. So if there's some node from this node to this other node, it doesn't automatically mean that there's an edge in the other direction. This would be useful, for example, for like a fixed wing airplane, right? It has to keep moving forward the whole time. It can't just stop and like reverse because it needs lift over its wings. And just to be kind of complete, there's also something called a mixed graph that has both undirected and directed. You can always convert that into a directed graph by just, for the ones that were undirected, just change them out for one edge going in either direction. But typically we assume either undirected or directed because of that. And that's about it. My soapbox for using graphs for motion planning. I have some soapboxes. This is one of them. So let's back up and let's think about numbers, right? Numbers are a tool for thinking about quantity. So 3 and 5 are numbers that have this relationship. 3 is less than 5, right? And 3 meters is less than 5 meters. 3 kilograms is less than 5 kilograms. And 3 eggs is less than 5 eggs. But the units really matter here, right? Like 3 meters is not the same as 3 kilograms. 5 kilograms is not the same as 5 eggs. And even the number 3 is different than 3 eggs, right? The number is like this abstract concept that we're using to reason about quantity of whatever we feel like. So because we have this abstract concept, we can define rules and stuff with that abstract concept, and then it's applicable to all of these different things like eggs and kilograms and meters, etc. So graphs are the same kind of theoretical abstract. They're similar to numbers in that sense. They're an abstract relationship, and they are the kind of correct mathematical tool for thinking about relationships, where numbers are for thinking about quantity, graphs are for thinking about relationships. And the same graph, like this right here, which is a mixed graph, could represent two completely different things, right? The same way that the same number could represent like 3 eggs or 3 kilograms, but the context really matters. This graph showing how different nodes are connected to each other, it could be the nodes on like a road network, and maybe we have some mountain pass where you're only allowed to drive in a certain counterclockwise direction around this mountain. It could also represent like a robot in its configuration space. Here I have X, Y, and theta, and for some reason, maybe the robot can only turn in one direction because it's got a busted wheel or something like that. And in this case, we can only go in this direction. So exact same graph can be used for reasoning about like motion on a road network or the motion in the robot's kind of abstract configuration space. As long as you kind of are willing to buy into that concept, then we can just define some general tools for graphs, and we can use them for planning on road networks, or we can use them for planning for robots in their configuration space, or a whole bunch of other things, just the same way like numbers, right? 3 and 5 we could use for eggs and kilograms and all this other stuff. oh, wow, I had nice little labels. Okay. So again, like the abstract concept of the graph that represents these different situations is not the same as those situations. And like the units matter and what each edge represents matters, but they result in the same graph. I'm not going to belabor this because I don't have enough time, but that's one soapbox. So I'm also going to gloss over this, but kind of tacking onto what I just said, if you read papers about graphs and stuff like that for robot planning, for motion planning, a lot of times we print stuff in 2D because it's easy to look at and read. And it looks a lot like the edges themselves are what the robot is actually moving along. Now that's only kind of true if the robot is a point robot in the real world, not only in the configuration space, but in the real world. And the robot has a certain property that it's able to translate in every single direction, and it can kind of like turn on a dime, which isn't like kind of valid for a lot of cases. So when you kind of read these papers and you look at what other people have done, just know that they're showing you a graph, and that graph could represent something way more complicated or useful, like a road network or something like that. So don't get tricked into thinking that the edge is what the robot is moving along, right? Like right here, the robot's not really moving along that edge. What it's moving along is this road, and we're representing the relationship between that position and that position on the road by, let's see which one, I guess this node and that edge. So the nodes are representing kind of positions, and the edge is representing like the road that connects those positions. But the edge itself is not actually the road, it's the abstract concept representing the road. Okay, so I'm gonna switch to some code now to motivate the next part a little bit. And I'm gonna show you two things. Oh, Matlab kind of barfed, that's okay. So come back to me. Okay, let's see if it'll run. Good. Okay, I'm going to show you two different kind of things. So here's a graph. This is the robot is actually thinking about how it's going to get from the circle to the X, the blue circle to the blue X, if you can see them up there. And this is its thought process, basically, of how can I get from one to the other. This is one way of doing it. I'm going to show you a whole bunch of other ways to do it today, but we're going to start with this one. And it's thinking still, saying, well, I could go up there, maybe I could. Okay, and then it found a way to get from kind of the starting place to the ending place. Now I'm going to change one thing very quickly. And if anybody's got good eyes, then they know what's going on. But I will tell you what's going on later. Here, I've changed one little thing. I changed a number, but that's changed one little thing in my code. Here is a different way of thinking about how to get from the circle to the X. And it seems like the thinking is very different, right? Anybody shout out like the main difference that they notice here, just the high level behavior difference? Yeah. Yeah, seems to be kind of gradually expanding. And the first one, shout it on out. What did that one look like it was kind of doing? If nobody wants to, I'll shout out. To me, at least, it looked like it was like very kind of random and haphazard the way it was like thinking about stuff, right? And look, this found a path too. That's great. They both found a path, and they both work. There's a difference between those two things, and those are essentially the exact same algorithm, but I'm using a different data structure to support kind of figuring out what do I want to explore next. And let me look at how much time I have, because I want to make sure that I stay within the allotted time. So if we go back to here, and now we talk about data structures. So because this is such a quick talk, I'm gonna kind of give away the spoiler at the end of this, right? So I showed you two searches. One was called depth first search. That was the first one. And the second one was called breadth first search. And they are the exact same algorithm, except the data structure that we're using to figure out kind of the order that we do everything in, based on kind of the order that we discover nodes in. I'm using a queue for one of them, and I'm using a stack for the other one. Now I'm going to tell you what a queue and a stack are, but these are data structures. And all I did between those two algorithms, I run the exact same code, but I use a different data structure. So that's kind of cool. So I got to gloss over this part, but I'm sure that everybody here knows about like basic data structures, right? Ints, floats, doubles, chars, and stuff like that, right? Like you ever code in a language that, you know, makes you define the type of data you're talking about. That's good. I'm sure you know, 99.9% of you, and if you don't, that's fine. But like the other folks probably, you know about arrays and vectors and matrices. These are different languages have different words for these things, right? But we have like just a bunch of data all in a row, and we can index it, right? Like to find out where it is. There's also linked lists and double linked lists. Those are getting a little more advanced as far as data structures go. If you haven't heard of those, that's fine. They're just different kind of ways to store a bunch of data than an array or a vector matrix, and they both kind of have applications that they're good for and applications that they're bad for. Then we have these other high-level data structures like the queue, the stack, and the heap that I'm going to talk about today, and then also some like trees and graphs and tons of other really awesome stuff if you're ever interested in that. There's some really, really cool data structures out there. But the queue is like a line. Queue is like, in the UK, they call getting in a line, getting in the queue. And so a queue is just like a line of stuff. And it's kind of you know how we all say, I'm going to go get a Kleenex, even though Kleenex is like one company that makes the hankies, and a whole bunch of other companies also make Kleenex. Well, queue is the same way. It's like there's a whole bunch of different types of queues, but if you say queue and you don't specify it's something different, then you can assume it's like a first in, first out queue. Which means the first thing in is the first thing out, just like you would be like a line, you know, at the grocery store. So there's a few different commands that you can use to like put stuff in this thing and take stuff out. I'm going to gloss over that again because I don't have a ton of time. But basically, there's ways to put stuff in it, and there's ways to take stuff out of it. And you don't get to control what comes out of it. It's just the thing at the front of the line comes out next whenever you say, like, give me the next thing. A stack, on the other hand, it's kind of different. It's like last in, first out, or first in, last out, whatever. You know, it's this inverse sort of relationship between your position and when you get to come out. So at least in my cupboard, usually, plates are in a stack where the one on the bottom sits there until somehow I use enough plates to get down to it, right? But like if I wash the dishes after getting halfway done, then I put the plates back on, and this one on the bottom just kind of languishes there for like a year and a half. You know, maybe eventually I have a party or something, and then we use them all, and then like this plate gets, you know, someplace else randomly. So that's a stack, and it means that exactly like the plates in my cupboard, right? Whatever we put in last is the next thing off. Okay, now there's graph search preliminaries. I'm gonna really go fast through this too, but as you may have noticed, there's different types of equals, right? There's the assignment equals, and there's the checking if two things are the same equals, right? Like I can say x equals 5, that puts 5 into x. Or I can say like 3 equals 4, and it might return false, right? So in this code, the assignment thing is a little arrow telling me I'm storing this thing in there. And it's not in the forward direction like a pointer would be if you code in C or anything like that. It's in the backward direction saying, take this thing and put it in that thing. The equals sign here is like equals equals or equals equals equals, depending on the language you're using, which is the Boolean function. So also, the way that I'm showing these algorithms are a little bit adjusted from standard, but under the hood, they're working very much the same way. That's what this kind of disclaimer relates to. Oh, also, we're like, yeah, we're kind of, if you were to implement this in practice, some of the properties like, do I live in a particular list or not? If I'm a node, I would just have a part of my data structure that's, you know, set to true or false, depending on if I'm in that or not. Or I could have a different integer saying like, if it's 1, I'm in some list. If it's 2, I'm in like a different list or whatever. I don't have to actually put stuff into like some container that's a list. That would be really inefficient. It would run very slowly. So but for thinking abstractly about the set of nodes that has a certain property of being in that list, that's how this code is going to show it, the pseudo code. We have a start wherever the robot's starting. We have a goal, wherever the robot wants to get to. And each node is going to maintain a list of its neighbors. I didn't talk about what a neighbor was really, but it's all of the nodes connected to me by an edge that, like the robot, if it were at me, it could get to these other nodes. Said a little bit better, if I'm a node and I'm representing a position in the world, and there's some other node connected to me that represents another position in the world, then the fact that there's an edge between us means that the robot can get from the first position in the world, represented by me, to the other position in the world, represented by my neighbor. Okay, parent now is a special neighbor that is the node from which I was discovered in this search. Breadth first search, depth first search, often abbreviated BFS and DFS. So breadth first search uses a queue, depth first search uses a stack. This is the basic algorithm for both of them, depending on what type of queue I'm using. Queue now, the variable queue, we often use to represent the concept of queue because it's, I guess, very onomatopoeic or something. But this could be the stack. It could be the first in, first out queue. And depending on what it is, we're going to get that very different behavior in those algorithms that you saw. So if it was the stack where the last thing on is the first thing off, then we get this totally random thing because it just kind of keeps going and going and going and going. And if we do the first in first out thing like a line at the grocery store, then everybody kind of gets their turn. And then the next nodes that we discover from there, we keep going. So let's look through this algorithm. So we're going to put the first node in, that's the start. And we're going to say we have some set of unvisited nodes. And again, we're not storing this in an actual set. This is like in the, each node just remembers, is it in the set or not? It's not like a array or anything like that. And then we're going to insert start into whatever type of queue we're using. And then we're going to say, okay, hey, queue, give me the thing that comes out of you next using this top function. And this means empty set. So as long as the queue, or it could be null if you feel like it, as long as the queue has stuff in it, then we're going to keep getting the next thing out. And for the thing that comes out, we're going to say, okay, do you have any neighbors that have not yet been explored yet or found? And if so, then we're going to put them in the queue, however they go in the queue. If we're using the queue at the grocery store sort of queue, then they go in the back of the line. If we're using the stack in my cupboard sort of queue, they go right on top. And then we also mark who the parent was, that we're the parent, I guess, for all the neighbors that we're discovering. If we happen to find the goal, then we're good, we return success. And if we don't find the goal after the queue has been completely exhausted, that means we can't get there. So we return failure. Okay, now knowing what you know, let's watch those two algorithms again. So I'll show you the first one first. This is the depth first search, and it's called depth first search because if we were to kind of like hold this up, like pick it up and hold it there so everything's dangling down, and each kind of the way that we discover new nodes is represented in some dangly down tree, then depth first search is just going as deep in that search as possible, which means it's going it just keeps going and going and going until it can't go anymore. And then it backs up until there was some other choice it could have made. And then it keeps going and going and going and going until it exhausts that one. As you can see here, it got to the end, and now it's backing up and it's like filling in kind of the other branches. Okay, now let's look at the breadth first search, which is using the kind of line at the grocery store sort of a queue. Oh, wait, I didn't do it the right way. I forgot to save it, I think. Let's stop. I don't have enough time. Oh, no, we'll have to wait for it, sorry. You've seen this before, I'm sorry. Now this is like the third time you've seen it, I guess. And keep in mind, like this is the thought process is using reason. Okay, there. These searches are kind of naive, right? We're just going one way or the other. And I will show you a better search next. But okay. Oh, that's my problem. Oh, stop it. Go away. Maybe that'll work. Okay. And then Okay, that was, I was changing the wrong parameter. Apologies. I should have been changing this one. There we go. Now this is the depth, now it's a small window. Oh, yeah, I shouldn't have done that. I am sorry, this is gonna be small this time. We'll watch it one more time. Wow, I'm really blowing the time here. Let's see. Okay, we still got 5 more minutes. I'm not gonna show you this again because I wanna move on, but you can see this is kind of, or nodes continue to be kind of expanded beyond themselves in the direction that they were discovered the first time. So everything is very orderly here. And there, we get to the end. Okay. But now that these windows are big, then the next thing I'm going to show you will work. Okay. Now, skipping that stuff. Now, there's another type of a data structure called a priority queue. And a priority queue, another word for that is called a heap. Priority queue means we're going to give everybody, like you know, like at the DMV, you get like a number, and that's when you're served. And these priority queue values can be kind of determined by anything. There's some ranking, and the line kind of reorders itself based on everybody's ranking. This is a max priority queue where the person with the highest number is in front. We're actually going to use a min priority queue or priority heap where the thing in front has the lowest value. Well, I was asking, okay, who has the lowest key value? They're the next thing that gets to come out. So it's like the lowest number at the DMB. They get to come out next. And priority queues or priority heaps are often represented using some under the hood data structure called a heap. It looks a lot like a heap of laundry, kind of. It's just this thing. And there's this cool property where everything in this heap has a lower key value than the stuff that's below it. And without going into too much detail, this allows us to very efficiently always get the thing with the minimum key value. And where like searching through an array or a linked list to find the thing with the lowest key value would take the amount of time proportional to the number of things in that list, this is way faster. It takes the amount of time proportional to log of the number of things in that list. Because if we do this really, really well, then the height of this thing is proportional to log of n, where n is the number of things stored in there. And we can add to it and we can remove from it, going at most kind of up and down twice. So, or all the way up and all the way down. So that is a really cool topic that I'd love to talk more about, but I'm not going to today. But just know, like, if you want to implement an algorithm like this, use one of these things because it will be so much faster. And you can find things that people have implemented online. Metric spaces. Oh, I'm going to skip over that. Metric spaces are great. They're a nice mathematical sort of thing that means that distance behaves the way that we all have come to know and love and respect. They have to have a few properties. The most important thing for this particular algorithm that I'm going to show you next is the triangle inequality, which means that going from x to z will never get shorter by going through some other point y. Okay, so Dijkstra's algorithm is where we are going to remember how much distance it took to get from the start to the current node. We're going to use that as a sorting key value in a priority queue, and then we will expand nodes in that particular order, which means that we have a nice kind of invariance thing that you can prove that you're guaranteed to get the shortest path. So if you want to find the shortest path on a graph, then Dijkstra's algorithm is the first algorithm that you should consider using for that. So let's watch Dijkstra's algorithm once. And we will say, yeah, 0. Okay, so at first glance, this may appear to be very close to kind of breadth first search. And Dijkstra's algorithm and breadth first search are actually equivalent if every single edge length is 1. If we're using edge lengths based on, let's pretend now that these are actually the trajectories that the robot can take. So this is actually like a road network. and so the robot is a point robot, and it is operating in this XY Euclidean space, and it is a holonomic robot that can turn on a dime, then all of these lengths are, whatever they appear to be. And we're expanding it in a way so that we're guaranteed to get the shortest path. And that's true to anywhere that we've kind of explored by the time we find the goal. So the shortest path from this node back is guaranteed to be, well, starting here, I guess, and getting to that node would be that way. But if we run until kind of, if we don't stop when we find the goal and we keep going, then we will find the shortest path to everywhere in this space. So I think I only have a couple minutes, 1 minute left. So 1 minute left is going to say, if you like all of that stuff, the next thing that you should look at is the A-star algorithm. I'm going to show you one more video and I'm going to be done. But there's other stuff in the talk. If you like this stuff, the A-star algorithm is going to use a focusing heuristic to guarantee that we might find a better, well, we'll find at least the shortest path, but we might find it a lot more quickly. So if we use a focusing heuristic, then we are using a slightly different key value in that priority queue. And the key value that we're using has to do with the amount of distance from the start to the current node, plus an estimate, like a rough estimate of the amount of distance left to get to the goal, just based on if we could beeline there. We don't know what the graph is going to be like in that part of the thing that we haven't explored, but we're going to assume optimistically that we could beeline there, and we end up expanding a whole lot less nodes. So that's it for my talk, because I'm out of time. But if you want to know about extensions to Dijkstra's algorithm and A-star, there's a couple in this talk. And if you want to know about extensions of that stuff, look for those algorithms that were actually in the title of the talk. That's it.